Hey, what is up everybody? It is Mr. Boylan and we are back for some more good times. In this video, what in the heck are we gonna do? We're gonna continue our study of how chemical equilibrium can be used to describe proton transfer reactions of acid-base chemistry. Breaking it down a little bit, first thing we're gonna do in this video is explain relative strengths of acids and bases based on molecular structure, interparticle forces or intermolecular forces, and solution equilibrium. And then two, we are going to generate or use a particulate representation. So get ready to bust out your art skills here of an acid or a base to explain the species or explain the thing that will have large versus small concentrations at equilibrium. Okay, so first, when we talk about a strong acid or a weak acid, what does that mean? Well, acid or base strength is measured by the size of the equilibrium constant K when it reacts with water. Now, whether or not it reacts with water is related to both the polarity and the strength of the bond between hydrogen and the acid anion. And again, remember when we're talking about equilibrium, we need to recognize that both the forward and the reverse reactions can occur. And then how we define strength is going to be dependent upon, well, are there a lot of products or a lot of reactants when we reach equilibrium? Now, it's important to recognize that the equilibrium constant for this reaction is often called the acid ionization constant, Ka. It's still a K, it's still an equilibrium constant, but we're just specifically talking about acids now, so we're going to use Ka. It's still a ratio of products to reactants. And the larger the Ka value is, the stronger that acid is. And so we need to think about, what does a large K value mean? Does that mean we have a lot of product, or does that mean we have a lot of reactant? So as you think about the equilibrium constant expression that I would write to represent placing this acid in water, I'm going to put my product concentrations over my reactant concentrations. Remember, I'm not including water because we don't include liquids in our equilibrium constant expression. They can't have concentrations. Now, in a strong acid, we're going to have a large Ka value. In other words, we're going to have a lot of product, or a strong acid is essentially going to put a lot of hydronium ions into solution. As you think about how we might represent this at the particulate level, recognize again that there's this sort of back and forth, but with a strong acid, we're going to have almost all product. And so notice we're going to have a bunch of ionized acid molecules. In other words, the hydrogens will have separated away from the acid molecules. Now, a strong acid or base ionizes completely in aqueous solution. 100% ionization, or pretty darn close. And so our equilibrium position lies really far to the right. We've got a lot of products, and they are indicated by really large Ka values. Strong acids also make really strong electrolytes because they have a lot of ions in solution. Notice that we won't even use an equilibrium arrow when it comes to describing strong acids because the reverse reaction is essentially non-existent. And so as you look at the general reaction for a strong acid in water and its corresponding equilibrium constant expression, we're going to get Ka values that are much larger than 1 for strong acids. So again, as you think about what we might see at the particulate level with a strong acid, recognize here we've got our equation set up for the strong acid. We're going to see a lot of these products form. We have large Ka values. And so we have a lot of these ions in solution. And so we're going to have really great electrolytes. Notice that the same is true for a strong base, except instead of forming hydronium ions and anions, we're going to form these cations and hydroxide ions. Again, really strong electrolytes. Okay, now weak acids or base, on the other hand, do not completely ionize. Usually we're talking less than 10%. In this case, the equilibrium position lies very far to the left. We've got a lot of original reactant molecules in solution, and we're indicated here by really small Ka values. They're generally weak electrolytes because we don't have a whole lot of ions in solution, and it's important to recognize that the vast majority of acids and bases are in fact weak acids and bases. As you think about the general reactions for either a weak acid or weak base with water, we're going to get a couple of equilibrium constant expressions that look sort of like what you see here. We're going to have Ka values that are much less than 1 because we don't have a lot of products formed. We have a lot of our original reactants in solution, not a whole lot of our products. So K value is much less than 1. So again, as you look at this general reaction for an acid, now we're going to think about the fact that we've got a weak acid. In other words, we're going to have a lot of our reactants at equilibrium. The reverse reaction is going to be favored. The values for equilibrium constant, or Ka, is going to be very small. Lots of reactant, not a whole lot of product. At the particulate level, as you try to visualize what's going on here, notice this time we've got a lot of unionized acid molecules in solution. Again, as we look at this particulate representation of a weak acid, notice that we've got a lot of these original unionized HA acid molecules left in solution. So it does form some hydronium ions. And so we do conduct electrical current still, but not nearly as strongly as, or intensely as, our strong acid. So your weak acids are generally considered weak electrolytes because they don't have as much ions in solution. All right, now let's take a look at a quick animation here that gives you an understanding of what's going on with strong versus weak acids. We're going to start with HCl, which is a very common example of a strong acid. You put it into solution and it completely ionizes into hydrogen ions or hydronium ions and the anion of the original acid molecule, a very strong electrolyte. Nitric acid is also a great example of a strong acid. You put this sucker into water, complete ionization into the hydrogen ion and the nitrate ion. Very strong electrolyte. We also have an example, though, of acetic acid, which is a weak acid. You put this sucker into water, notice what happens. It's a weak acid solution, so we don't have a whole lot of ionization. We do, but then we have that reverse reaction. Again, as you think about acetic acid, we have a lot of original acid molecules, some ionization, but then a lot more of the neutral acid molecules in solution. Keep in mind, we can also observe this with bases. If you take a look at any of the classic strong bases, which you'll see with things like sodium hydroxide, potassium hydroxide, or calcium hydroxide, when you put these bases into solution, they're going to completely ionize. They're going to have very large K values because they have a lot of ion products in solution. Stay separated, really large K values, and they're going to be really good conductors of electrical current because they've got all these ions left in solution. Ammonia, however, is a great example of a weak base, something that will have relatively little ions in solution. In other words, the reactants are going to be favored. We do see some ionization, but again, notice we see that return to the original reactant molecules. So a weak base, a weak electrolyte. Boom. As always, take a quick moment to check out the references to see where I pulled some of those images and video from. You can find this in the info beneath the video.